I forgot to close this one. Okay, so right now the first step here, I uploaded, but I just make it, y'all cannot view it only. Okay, let me make it available under content, workshop. Make it available. Okay, so this is RMD file, our markdown file. So your first step here, always downloaded the required libraries that needed. So right now for our data set here, we will be looking at this Boston data set, which is about the housing values in the suburbs of Boston. So this data set consists of 506 rows, which means that the total number of observations here is 506 observations, with 14 columns here means 14 variables. Okay, so this data set is available under a package called MASS, M-A-S-S. So for those who have not installed this package earlier, you need to go to install a package. Okay, you click on the packages and you type MASS, MASS, then you just install this package. Right, so after you install this package here, another thing that we want to play here today will be using this CORRPLOT. This is to visualize your correlation matrix. Okay, so there will be two packages needed for today's section. The first one is MASS, MASS. The second one is on this CORRPLOT, stand for correlation plot. Okay, so after you install both packages, before we run any function, then we have to call out the library functions. Okay, so this library mass and the library for your correlation plots. Okay, so this one, I'm trying to run it chunk by chunk. Here means that right now under my gray color boxes here, okay, this is my first chunk. I'm going to just click this run current chunk. Okay, so this one they just mentioned to you your core plot 0.92 loaded, right? So my step 2 here now, I want to look and explore my data set. So as mentioned just now, for today's workshop, we are going to look at this Boston data set. So you just call out this data and the name of your data set. So if you are using this, the head, okay, the head function in R means you are going to view the first 6 rows of your data set. So if you want to look at the last 6 rows, then you can just use the function TAIL, T-A-I-L. Okay, that is for your last 6 observation. For the first 6 observation, we'll be using this function head, H-E-A-D. Okay, so the next one, to look at the structure of the variable, the function is str. So why we need to know the structure of the variable basically is we need to look at the types of the variable, whether they store it as a numeric or as integer or as a categorical variable. Okay, then after that, we always look at the summary of your data set before you do anything. Okay, so now if I try to run this, my second chunk here, all right, so either you look at under your this part or you go down to your console here also can. Okay, so this one the head, the view show you nothing, right? Then this one, the structure here, so they tells you, okay, for this one, CRIM. Okay, if you want to know more information about this data set, right, then you go back to your help function here and you search for this BOSTON. Okay, on this data set. So there is a description of your data set. So CRIM here is stand for the per capita crime rate by town. All right. So you have the next variable. ZN here is a proportion of residential land zoned for lots over 25,000 square feet. So basically for this data set, right, our target variable or our interest is on the last column, which is the median value of owner-occupied homes in thousands. Okay, this one, the MEDV, will be our target variable. And the other 13 variables will become our inputs or our explanatory variable or predictors or regressors. Okay. So by looking at the summary of this data set here, we roughly know that, okay, the median value, which is my response variable here, the minimum value is 5,000, maximum will be 50,000, and for their distribution, right, when the mean and the median are quite close, we can roughly know that they are quite bell-shaped curve. Okay, so this one is by looking at numbers, or you can try to visualize them by using either a histogram or a box plot before you proceed with any modeling. So why you need to proceed by checking on their summary and the distributions here, because if we want to apply for either simple linear or multiple linear regression, we assume that our random error follow a normal distributions. In other words, your target variable, which is your y here, should also follow a normal distribution. Okay. So in that case, that one I'm not showing you on how to do the plotting. That one you have learned it in your chapter 1, right? So I leave it as your exercises. So right now, during the Tuesday class, we start with by checking on the multi-collinearity issue. One of the method is by looking at their correlation matrix, right? The easiest way. So first thing first here, we need to calculate what is the correlations. Okay, the correlations for my data set. So if you move your cursor to this COR here, that tells you they are trying to calculating the X and Y. Okay, the methods either using Pearson, Kandastar, or Spearman's rule here. So in this case, we just treat all our variables here as numbers or integer only when you want to calculate their correlations. And when they are in numbers, right, quantitative or continuous variables here, we will be using Pearson correlation coefficients, which is what we have defined in our chapter 1, chapter 2, and chapter 4. The correlation coefficients that we are using here is the Pearson correlations. Okay, so the function in R here will be just this COR functions in order to calculate your correlation matrix. So after that, I want to visualize it, right? So how to visualize it? So I store my correlation matrix here. I give it a name as COR underscore matrix. So after that, I'll be using this function also, CORRPLOT, under the same name of the package. So here is my correlation matrix. So the methods here, okay, for the methods, you can put in like as a color, as a size, or as a number, or there will be many methods that you can use. So here they got mention ellipse, square, shade, color, pie, and so on and so forth. So you can choose which method that you want to display for your correlation matrix when you want to visualize them. Okay, and the type here, whether you want to present a full correlation matrix, or I just want to show a lower triangle matrix or the upper triangle matrix. So here I'm choosing to show it as the upper. So in that case, I got the graph something like this, right? Okay, let me try to run it again. So in that case, okay, so there is an indicator functions here where let me maximize it. Okay, their indicator here, when the color is getting closer to the white color, means that there will be no correlations. And the color getting darker blue indicates that their correlation is getting stronger to +1. Getting darker color to the red or brown color is a negative correlations. Okay, so right now again our target variable or our response is the last column, which is the MEDV. Okay, so from these visualizations here, we know that MEDV is having a quite strong negative correlation with this LSTAT. Okay, because their color is getting closer to -0.8. Okay, you match the color with their indicator here, and it will be a positive correlation with this RM. Okay, and their correlation is somewhere around 0.7 or 0.8 here. Okay, and another thing here, the white color here may be quite very weak correlation will be with this CHAS and also the DIS. Their correlation are quite weak. Okay, right? The visualization part for your correlation matrix. Okay, so the next one here is, okay, let us start with our full model. Okay, this is what you have learned in your chapter 3 also. So for our full model here, we are going to fit it using a multiple linear regression model. Therefore, the function we will be using here will be just this LM function, stand for linear model. So your formula here will be just MEDV, which is your response variable. Tilde here means it depends on. Again, a dot here means that I'm going to make use all my remaining variables, which will be 13 variables. So my 14 here is including the last column, which is this one, MEDV. So this one is my response. So I'm going to model it based on the column 1 until column 13. All right. So my data here is this Boston data set. So I call my model here as my full model. Then I'll be looking at the summary of my full model. So when I try to run this one, okay, this is my summary output. Okay, again, let me enlarge it. So what we try to observe from this summary output for the full model here, first one, we will be looking at the last row, which is my F-test statistic. So this one is testing based on my overall model, or we call it as our full model here. It must be significant. Okay, then only you can proceed with the next hypothesis testing. Okay, so from the output here, either you will be using the rejection region approach or using the p-value approach. You reach out to the same conclusion that this model is significant. Means that at least one of the regressor is contribute significantly to your model. Okay, then from this part, right, the coefficients here, we notice that some of the variables, they are not really contribute significantly to the model. So for example, this one, the variable INDUS is not significant. The next one, the age, AGE, also not significant, right? Okay. So in that case, if we want to perform the variable selection method, means that we try to obtain a reduced model. Instead of using full model, we want to just choose a subset of the significant variables that need to be considered in. Okay, so the steps here is, okay, let's say we will be using this backward elimination method based on p-value criteria. Okay, so now the question here is, from our full model, we want to obtain the best subset model by consider backward elimination method. And for the backward elimination method, our selection criteria will be based on their p-value. Okay, so in that case, we will be using this drop one function. Okay, so how this drop one function it works here? So you'll be using drop one. Okay, inside here will be your full model. Okay, and the test here will be using this F test. Okay, so if you try to run this one, and they're showing you that, okay, basically about the same output as just now. So you will be looking at the last column here, where this one, the edge, show you with their highest p-value. So when the p-value is greater than your alpha, which is 0.05, we say that it is not significant. So for the backward elimination method, we try to remove those insignificant variables, and we start by remove the most insignificant, which is the h for this case. Okay, so the h is the least significant by the f-test, so it will be removed from the model. Right? So after you remove that, right? So in that case, we'll be using drop one function again. You're going to update your model based on the full model, but here, okay, we minus with h. So this one, a dot here means that we are using 13 variables, but then we minus the h. Okay, so if you try to update your existing model here, so right now, you still have one more, which is not significant. So for backward elimination method, it will keep removing those insignificant variables until the remaining variables that remain in your existing model, they contribute significantly. Then the process will terminate here, will end here. Or all those variables that have been added being removed, that means that you have nothing in your model, then the process must stop. Okay, so the process will stop when those insignificant has been removed from your model. So right now, this one is still not significant. So we need to drop this indus variable and then update to your latest model here again. So now this one is the least significance. Therefore, we are going to use this drop one function again, update your model. Now it's minus with this variable. Okay. So after that here, they tell you that, okay, this warning here because right now you compare this output with the previous one, they still show you their p-value here when there will be some insignificant variable. But right now, this one, they only showing you their AIC or their residual sum of square. Okay, so in that case, that means that all the existing variable that provided for your latest model here, they contribute significantly. Okay, so in that case, your final model here will be based on this crime, ZN, Charles, Knox, RM, and so on and so forth, without H and without INDUS. Okay, so now all variables are significant at 5% significance level. So there are two variables that are being removed from our example here. Okay, so you can also obtain the summary of your final fitted model here, which is based on this one. So if you look at the summary here, their p-value for the overall model is still significant with their respective V1 and V2. The R square value 0.7406, adjusted R square 0.7348. Then after that, for each individual t-test here, all are significant. Okay, so basically this is how it works for the backward elimination method, and there will be a lot of different methods that we can be used here. So for R here, the one that I'm showing you here is we will be using this drop one function, means that we try to do it manually one by one. Of course, there will be other functions that you can try to explore yourself. Like, for example, you can using the AIC methods. That is, the elimination method is based on your AIC criteria. So that one, the function that normally I use will be the step AIC. Okay, so that one I leave you to explore by yourself. So right now, before we end this one. Okay, we just try to knit it into the Word document so we can see the whole picture. So for those, are you all able to run it by yourself? The coding part here. So once you knit it into the R document, you should have something like this one, right? So after that, you can adding in your explanations here and there, or you adding in your explanation using your RMD file. Okay, so far so good. Any questions? What CBT is what? Okay, for your CBT, right? You can bring in your hard copy, but you are not allowed to Google search anything.